thank you all for being here today. We have David Steinmann today presenting Object-Centric Concept Bottleneck models. David is a PhD candidate at the AI and Machine Learning group in TU Darmstadt. And yeah, today we're here to know more about your work. And yeah, please take it away.
Yeah, thanks for having me here. I'm David, and yeah, as Peter already said, I'm going to present my recent work, Object-Centric Concept Bottlenecks, which has been a news paper from last year and was joint work together with Wolf and Antonio. I mean, you've probably heard it quite a bit already, but still, let me give a brief introduction about CBMs. So the general idea of CBMs, or general premise of CBMs, is that we want to have interpretable models, or at least somewhat interpretable models. Instead of solving a task in a black box fashion end to end, we compose our prediction into two different steps. First, we compute some concept encoding, some concept representation from the input, and then we predict the output based on this input in an interpretable fashion. This allows us, given that the concepts themselves are somewhat understandable for humans, that we can check, we can verify whether the concept representation makes sense, whether it's accurate. And then if the predictor itself is interpretable, then we can also trace the steps or the reasoning steps from concept representation to output in a understandable way as well. So this general idea of CBMs has been getting more and more popular in the recent years. But the general question, I guess, is quite obvious: is what actually are concepts, or what should concepts be? And even if there's now quite a few papers in this area, what specifically a concept should be or should not be is still highly debatable. Also depends a lot on the task and what you want to solve, what modality you have. So yeah, that is definitely not a already clear thing. And today I want to talk a bit more specifically about visual concepts, or about concepts in visual data, let's say. So if we look at this image, for example, there's a lot of information present in this image. And this information has kind of different levels, different structure, different connections, everything. So for example, we have general information. Like this picture has been taken outside. There's a lot of grass on the floor. The sun is shining. It's a nice weather. That's all general level information, scene level information. Then we could say, okay, we have a lot of objects within the scene. So for example, we have a lot of humans in the front. We have a sheep. We have trees in the background. We have cars. All of these are different individual objects, individual entities within the scene. And then we have maybe some representation or some information tied to these objects. So for example, the person in the front is wearing turquoise clothing and has dark hair. So the next step, or the next level of information, would be object level information. If we go even one step further, we can talk now about relations between objects. So for example, there's the person is petting the sheep, or in the background there's a person walking a dog. So this goes even further and now specifies how objects interact with each other. And if we want to go even further, we could, for example, say, okay, there's maybe some spatial things, like spatial relations as a subpart of the total relations. Like people are, spatial relations between objects, like things like foreground, background, occlusions, and stuff like that. So the general idea here is there's a lot of information present in this image. And a lot of information might be useful to our task or might not be useful, depending on what we want to do. But if we want to do something a bit more complex, let's say, having inherent structure in our concept representations might be a good thing, because we might know, okay, objects belong to, or concepts of objects belong together, relations are between objects and stuff like that. However, if we look at CBMs right now, most CBMs have just the concept representation of the concept set as, in fact, a set. So it's just a big number of potential concepts, and these concepts describe something about the image. They don't have any specific structure within them. And this limits greatly what we can actually achieve with this concept representation. So first of all, it mixes information from the different levels I talked about before, but it also mixes concepts of of different objects, for example, together. Like the turquoise clothing is not specifically belonging to one person anymore, but it's just like one thing of the whole image. So that's, I would say, is the main thing we want to tackle in this work, or we try to tackle in this work, let's say. So to kind of counteract this, we introduced object-centric concept bottlenecks, where we combine kind of, let's say, the power of recent pre-trained object detection approaches with CBMs to enable more object-centric representations and allow for grounding of information to specific entities, for grouping of concepts, and all the other things I said I mentioned before. So yeah, that's kind of the general idea of what we want to achieve. And now let's go a bit more into detail about how we actually achieve this. So here it's kind of a partly overview of our method, and the first part is basically the same structure of a standard CBM. So we have our input image. We take this image and input it in what we call the concept discovery module, or it could also be concept encoder, concept extractor, different terms for this. Specifically here, we use the recent work Splice, which is a clip-based concept extractor, which has a large general purpose vocabulary of potential concepts, matches the clip similarity of the text encodings with the image encoding, and then importantly specifies the output concept representations. So while it has a very general purpose vocabulary, the resulting concept representation is sparse, so that we don't have a big and non-interpretable concept space. Then the concept representation is kind of put into the predictor, and the output is presented. So far, so good. That's like the default CBM. How do now the objects come into play? And this happens by including this object proposal kind of step. So we take a recent object detector, for example, a mask RCNN or a SAM for segmentations, and let it generate object proposals for the given image. What an object proposal is essentially a bounding box. So it's a bounding box for different objects, or for potential objects. However, these bounding boxes, if you take them directly, are usually quite noisy. So like you might have a lot of bounding boxes which overlap, a lot of bounding boxes which just find something small in the background, which just might be an object, but might not be. So to make this a bit more usable, we go through what we call the proposal refinement. So that's essentially, it's like 3 big steps. So first, we filter the proposals by size and certainty. So as I said, very small proposals are not really useful to us most of the time because they don't carry that much information, or extracting the information is difficult. Very large proposals are basically the same as the whole image, so they also don't hold much benefit anymore. And then most object detectors also provide some type of certainty or some type of score, how well the proposal or the detection actually worked there. And we take this and set a minimum threshold so that we kind of get rid of some of the noise already. Then we remove overlapping bounding boxes, similar to non-maximum suppression from the object detection field, which basically means that we remove proposals with high overlap, with a high intersection of a union among each other. And lastly, we only limit the amount of proposals up to a total number of k. So, I mean, in theory, having more objects means, or generally a more expressive concept representation. However, also at some point, our predictor has to handle these objects. And if we add more and more objects, at some point, it also gets more and more difficult for the predictor to actually work with these. So we said, okay, we limit up to k equals 10 in our case, which is a reasonable trade-off between expressivity, but also reasonably for the processor. So then, after the proposal refinement, we have our refined set of bounding boxes, and we crop the image to these bounding boxes and get then as many image crops as we had proposals before, and input these crops into our concept discovery module as well. So, yeah, we thus can get concept representation for each of the objects we have found. So we get additional concept vectors, and the next step then is to aggregate them together to get a combined concept representation. The most naive thing, or the simplest approach for this is just concatenating them. This has the advantage that we have like kind of full traceability. We know for every concept, we know to which object it belongs. However, it also scales linearly with the number of objects. And if we have a lot of potential concepts and a lot of potential objects, the input space for the predictor gets quite large, which might make it difficult to train if we have not that many data points. To kind of have not a linearly increasing concept space, but like a fixed size concept space, we have several other aggregation methods which we explored. So this includes max, sum, or count pooling. Each of these confine or compress the total concept representation into one single vector of a fixed size, equals to the number of concepts overall, and either takes the maximum per concept activation, the sum of the per concept activations, or the count of non-zero concept activations, while the last one being a kind of discretization, kind of a hard bottleneck, if you say. And as a further exploration, we also combine the sum and the count pooling to have kind of both informations about the discrete counts, which gives us direct information about, okay, this kind of there are three people in the image, with kind of the, let's say, soft certainties about how much the individual human things where all human concepts were activated. So as a kind of a middle ground between sum and count. Yeah, like these different aggregation methods all in the end produce a combined concept representation C, which is then used to train the predictor to predict the output. In our case, it's a linear layer, which is just like for the sake of interpretability. So that's the overview of the OCB framework. Just to briefly recap, we first take the image, we combine the full image with some object proposals and then crops of the object proposals, and discover concepts for each of these elements. Then we aggregate these concepts into a combined concept space and use this concept space for prediction of the output. So far so good, but how well did it actually work? How good does this actually perform? We evaluated OCB on several downstream tasks in, first of all, in downstream performance, so like an accuracy for single label tasks or mean average precision for multi-label tasks. And if you, for example, look at the different multi-label tasks here, we can see that OCB outperforms the CBM baseline models with different or for different configurations of OCB, and significantly narrows the gap to the completely black box clip plus MLT baseline or reference line, let's say, for all data sets. Also, if we look at single label tasks, we have, first of all, we have Sun, which is a scene understanding data set. So it has a lot of classes like desert, mountain, snowfield, lake, stuff like this, where naturally objects don't help that much. Like, I mean, you could potentially find objects which help in scene understanding tasks, but what one naturally thinks of as an object is like so often something which is not really beneficial for like these large image scale scenes. So naturally also the adding OCB to this data set doesn't really change a lot. Like it improves the performance like marginally, mostly because there's a couple of classes where objects help somewhat, but basically it doesn't hurt. And for the second data set here, which is CocoLogic, that's a combined or a data set which combines visual understanding with kind of logical reasoning based on objects within the images. And here we can see that OCB substantially outperforms the baselines and even can outperform the clip plus MLP black box model if objects are really relevant. So what we also explored is different object detectors. So like I told you earlier that we used mask RCNN or SAM, and in this case, mask RCNN is a more like specific or specialized detector because the data sets are either based on Coco or Pascal, which is somewhat similar to Coco. So we, as in this case, mask RCNN is somewhat equivalent to having like in-domain specialized concept detector. However, we also explored using SAM as a general purpose detector. And even if the in-domain detector works better than the general purpose detector, which is somewhat to be expected, OCB still outperforms the other methods or the other approaches if we have only access to a general purpose detector. So far, so good. Earlier, I talked about different aggregation methods, and we also explored how well these aggregation methods work. And here now I have a plot with a lot of different colors and a lot of different bars, and unfortunately not as clear of a message as for the table before. What we thought of is that there's actually no really clear aggregation method which performs best across all data sets. But depending on the task at hand and the dataset, kind of dataset structure, I guess, different aggregation methods perform generally better or worse. Overall, max and sum are quite good as a baseline to start at, but exploring other choices also is reasonable. And what is also being important to being said that even while the aggregation methods perform differently, they basically every time also still outperform the baseline. So while there's gains to get by exploring, getting just the sum or a max in all cases works better than not having objects at all. What we also explored a bit more in detail is about how many objects should we actually aggregate. And here you can see the performance of the downstream task. So mean average position or accuracy compared to the total number of objects is K for the refinement. And what we can see, first of all, is that for all object-centric tasks, generally adding more objects improves performance. So for the Coco variants and for Pascal, adding more objects increases performance. And what we also can see is if we take Sun, then adding more than one or two objects doesn't help anymore because there aren't that many objects within the images which actually correspond to the task. And adding more objects beyond that just makes concept encodings more noisy and makes it more difficult to actually solve the task. So adding more objects naturally doesn't really help here. The most interesting case is Coco logic, where adding up to 3 objects improves performance, but going beyond that then decreases it again. And that is most likely due to the nature of the task Coco logic itself, because it requires sometimes precise counting of objects, for example, or very precise information. And if we then add more and more objects and potentially increase the or accept that we get less quality proposals or more noisy proposals, this task is more sensitive towards that. So if we have a task where we need precise amount of object information, very non-noisy object information, adding too many object proposals can be detrimental again. So this was all kind of qualitative. So we have, unfortunately, don't really have quantitative interpretability experiments. However, what I can show you is at least some qualitative examples of how OCB changes or improves the concept representation, the concept level explanations of a model. So if we look at the first example here, so the top row, in the full image, we have examples like dinner, broccoli, plated, seafood, or vegetarian, which all make sense and describe the picture quite well. However, if we now look at the concepts which we get for different objects, we actually enrich our concept space more. So it's probably difficult to see, but the first object is kind of the bottom of a wine glass. And what the model then adds is concepts like wine or champagne, which describe that there's more information which has not been presented in the image level concepts. Similarly, for the second object, where we add fork or cutlery to the general concept space. And while the third concept or the third object doesn't add many more concepts, it very precisely refines like kale, broccoli, or asparagus as potential vegetables of this dish and confines them to a very specific region of the input image. The second example, on the other hand, doesn't provide us with new concepts per se by adding objects. However, it gives us a different kind of information. Because if we look at the full image and at the concepts there, we see, okay, pelican, swans, seascape, geese. So there's some kind of birds, and we have some kind of a seaside, which makes sense. Also, it's accurate. However, it doesn't tell the whole story, because from the full image concepts, we don't know how many birds there are. We know just there is at least one, maybe multiple, but we don't know specifics. If we now take the two detected objects and see, okay, for every of the 2 objects, we have the concept pelican as well. We know, okay, there are 2 pelicans in this image, which is way more specific than having, okay, 1 or multiple. Yeah, so like that's the kind of 2 main benefits of the concept level, the object level explanations in CBM. So it can enrich the representation with specific object level concepts, and it can also give us more structured information and more, which goes more into object counting, and it thus makes the information we have more precise. However, there are also some cases in which this can kind of backfire. So some failure cases here are that we can have, for example, duplicated object proposals. So if we have very large objects, then it might be that at some point the filtering of the intersection of a union doesn't collect all the different object proposals anymore, and we could have multiple proposals of the same object within our object proposals, which would result in the model detecting 2 airplanes in this image instead of just the one being there. And on the other hand, also adding this object-centric, I guess, prior into our model results in the model finding more concepts which represent the objects which we are most likely to find. So if our object detectors are trying to find humans in images, then we are going to add more human concepts to our concept space, even if that might not be necessary or even helpful to solve the task. So this is the Snowfield task, the Snowfield class of the sun dataset, of the scene understanding dataset. And in this case, the object detector adds the human and the human level concepts to this class. And this might result in some cases to spurious associations or spurious correlations, where we specifically bias our model to include more concepts from objects which our object detectors can find. Which again is a kind of a remark that the object detector we have is beneficial if it, to some extent at least, is aligned with the task we want to solve. Okay, so that's for the qualitative examples of OCB. And there's kind of like one last thing I want to talk about for the paper in general, but also for the CBM field overall. That's kind of, why do we actually want to do this? I mean, I motivated it in the beginning with like, we have visual scenes with very complex information, a lot of information, which we can get way more out if we have structure. But if we do things like, I don't know, if we solve tasks like CUP or ImageNet or CellFA, where we just have like one prominent image within, one prominent object within an image, and our classification is solely based on this object, then object-centric or in general more structured representation don't help us a lot. So I guess also the general motivation for OCB is to move towards more complex tasks, move towards being able to solve more interesting and complex applications with CBMs. However, this while this is a good, like, let's say, general goal, also on the other hand, the data sets for this are also kind of necessary to test and develop methods. And that's why we introduced the CocoLogic dataset within the paper. And CocoLogic is a dataset which kind of is designed to bridge logical reasoning and visual understanding. So it has a confined and structured classification task, which is based on logical rules of object occurrences. So it's kind of in a middle ground between, we want some logic task, we want some logic information, but we want it to be on real images. However, we don't want yet to the full complexity of, for example, open word, open answer VQA, also, or visual question answering. So it's kind of like an in-between between even more general tasks and having just like single label image classification. And OCB includes classes, for example, like this pair of pets class in the top right, where you can where you have to have two objects of either cat, bird, or dog. So you have like to have two of these potential pets, but not, for example, not all three of them. And the bottom class is another example of the animal meets traffic class, where we have to have different animals, for example, sheep or cows or horses meeting either a bus or different traffic objects. So these are just two examples of the classes. And yeah, the general idea of the data set is stepping in between very precise single label classifications and very open VQA tasks on the other hand. Good. With that being said, to conclude the task, the talk, not the task per se, OCB is designed to bring object-centric representations to concept bottlenecks, and thus generating more expressive and interpretable concept spaces. And yeah, I hope that I could make you all interested in this general direction, and I'm open for any questions or remarks.
We appreciate it. If anyone has a question, feel free to raise your hand and just unmute yourself and ask the question. A few of my own, but I'll let others ask her. Okay, Pietro.
Hi, David. Thank you, first of all, for a great talk. I have a few questions. I will start with one. Okay, the first one is, have you considered or experimented so far, or like, is the dataset supporting also more than unary concepts, like concepts that involve more than one entity, or more than one object? Not just a property or a single object, like the color of an object, but whether an object is interacting with another one. Like you mentioned this at the beginning of the talk, but I was wondering whether you played with it.
That's a good point. In this work, we have focused on unary concepts, I guess, or on just object or object properties. I would say going to relations is the logical next step, but we started with the objects themselves as first.
Okay, but is the dataset CocoLogix? Does the dataset CocoLogix support also binary or more than like n-ary concepts annotations? Like that, do we have n-ary concepts annotations here, or just?
I mean, the dataset has, I guess, like if you consider the classes as, I mean, there are 10 classes, and these classes are all based on occurrences of objects and logical formulas of these occurrences. For example, we have this here with the exactly 2 out of 3 categories, or we have this. We have also things where rules where concept or objects are supposed to not appear, or like XOR things, but we don't have like specific relations between objects or object types.
I see.
Also, as a slight remark, an updated version of this dataset we also right now in the process of making, which also includes then I would say more future version where like real data scarcity is also can also be explored, and they say, okay, how few examples can we actually use to find these rules.
I don't want to monopolize this. No one's talking about this much, but I kind of. Yeah, I actually have a question on the sort of parse side of things. So please correct me if I'm wrong, but is the filtering slash the candidate selection side of things is fully agnostic of the task and the model that comes afterwards, right?
Yeah.
The
right now,
refinement.
Yeah. Right now, the object or the first part here, the object proposals are independent of the task. I mean, as long as you have an object detector with which is like pre-trained in general. Like,
once you put say the concatenation mode, so when you aggregate them, just concatenating the different parts and the bottleneck in all the different parts, is there a hierarchy between the different parts, or like? Because I'm curious to see, because if the model always gets parts and those parts could be from anywhere, and there's no relation between any part except that the first bottleneck is always the full image. I'm curious why it learns, because that bottleneck in the middle could be anything, right? It could be from any part of the image, and it has no connection. The model does not understand how it relates to the different other parts, right? So I was curious if you looked into adding some structure would help, or like, for example, how important was the full image? If you remove the full image from the thing as one of the representations, how would it work?
We have explored removing the full image, which generally doesn't improve performance or even hurts performance, because there are still quite some concepts which, I mean, if we have objects, we crop the image to the object, which removes quite a bit of the general scene understanding concepts. So the full image concepts are like beneficial still. Besides that, the task we have here still, like as Pietro already mentioned or asked about, we don't really have tasks yet that require a lot of relational knowledge. So like we don't yet have included specific structure between the objects, which I would say is another logical next step. I guess it goes in the direction of the relations with a different spin of how to add this structure. I would say if we want to go to more complex tasks with CBMs, like adding structure is essential, or adding structure between the objects is essential. However, we haven't really explored it yet.
This is something really interesting here. Like you could, if the refinement particularly could be more task aware, so there's a learnable component to it. Like for example, even the task of counting sheep, something like that. If your number of proposals is constrained to a fixed number that you decided during training, sometimes the model may choose certain candidates over others because it's useful for a task, right? If there's a lot of sheep and it realizes that there's many of them, like maybe I'll just filter those things out instead of background things I use those for my current task for sort of reducing the confidence that I have in that particular task. It could be quite interesting to try to see if you could make the refinement get a bit more aware of the task.
I think that also gets even more interesting in the for example, in the CocoLogic dataset, or in the future version of that specifically. We also explored, for example, like using some VLMs there, and for the future version. And like while they have some, like the general object detection of them is quite good, like having the lack of knowing what objects to actually kind of propose or like include for potential rules or potential further processing to get the classes is an important or a big difficulty of such tasks overall, let's say. Yep.
Sorry, I have a related question to what Matteo asked. Like similar to the object proposal, also the aggregation could be task aware. No, you try different aggregations, and I guess different aggregations. Like if the aggregation, the kind of aggregation is learnable, or like a parameterized in some way from such that it can be learned. Depending on the task, as you said, you might actually find which aggregation works best. Like I guess, like for max and min, you're almost modeling quantifiers, no? The existence or the exist quantifier for all quantifiers. So depending on the kind of task, you may need one or the other or both. So I'm wondering also that, like,
I mean, in the task we explored here, to be fair, like most of them, like it's either like an exact count for the CocoLogic at most, or otherwise it's just like whether it exists or not. In most cases, like different types of quantifiers was not yet necessary to solve these tasks. But yeah, like going towards either a more learnable aggregation or also towards like just incorporating that information better is definitely also an interesting or potential next steps. I mean, also what we explore or what we have learned during the process since then is while concatenation itself, I mean, that's in theory that's the ideal thing. Like concatenating just gives you all the information for the interpretability for the predictor. However, I mean, it also scales the worst. That's the problem. And training the predictor is specifically if you have a large but sparse concept space gets way more difficult for concat than for the other aggregations because it gets even larger and even more sparse. So if you have more information about what potential objects you can or what potential concepts you are interested in, and can reduce the size of the concept space so that you don't have a very large but very sparse concept space, but a denser and more densely activated concept space, then concat suddenly also gets a lot better compared to the other aggregations. So that, I guess, goes back to what you already said, that like having a task-aware aggregation or at least learning the aggregation is also potentially a very good step to go to.
Yeah. Related to this, I'm wondering whether the semantics of these aggregators may break in some cases. Like I'm thinking, like you mentioned counting, but what if you have a concept like height? which is continuous. No, what does it mean to
Yep.
count things in this
Yep.
case? So yeah, what kind of aggregations in this case could be useful?
True.
Any other questions? Michael, go for it.
Yeah, thanks. Thank you, David, for presenting this. It's really interesting. And I agree with the premise for the work, which was that, oh, with regular CBMs, you have this essentially bundle of concepts, right? That's flat, it's non-associative, and somehow we want to have some structure on that. But as a critique, looking at this, it doesn't seem like we really resolved that issue, right? Because post-aggregation, for any aggregation method other than concat, we sort of do end up with this bundle of concepts again, right? And it's different than a typical CBM because it's at least weighted somehow, right, by number of objects that the concept applies to. But still, it's just flat, non-associative bundle of concepts.
To some extent, yes. However, what is also like an important part for this here is that the concept discovery, or the concept extractor, I guess, we used is you presents very sparse concepts. So unless unless there's objects which are very, very similar in the concept space, you have as long as you don't have too much overlap, you can directly trace the objects still back, even if you aggregate into a single concept space, which still, as to be fair, still breaks down. For example, if you have 10 different sheep or 10 different humans, and you want to understand which human has or one human has one color of hair color, and this influences the prediction differently, then at some point the traceability gets lost. Yes.
I
So
see.
yeah, so it doesn't resolve this fully.
Right, and I'm trying to just think about how this method actually still does have advantages over CBMs and how to leverage that. And in one way, after your proposal refinement and then concept discovery for the bounding boxes, right, the cropped images, you all of a sudden have something that didn't exist in regular CBMs, which is localized concepts, right? And immediately you throw away that locality. I would like to see you keep that somehow, right? Have each one of those bounding box concept vectors, labeled with the bounding box it came from, right? Continue associating it with that locality.
Yeah, I mean, I guess that is very similar to continuing to associate with the same object, right?
Right, and then maybe instead of just aggregating them, you could have a secondary, how do I say, a model which learns those binary relations we were talking about. And that model is assisted by the fact that we have localized concepts now. And I feel like that's a way we could really leverage your design and learn these more detailed, more difficult tasks that maybe have binary relations.
If I understand what you're saying, Michael, is that after the aggregation, there's no way to the concept representation is it looks as it was generated by just a single object, as the full image.
Right, exactly, as this method's currently written. But I really see potential here for keeping that locality data and leveraging it to say, okay, we don't just have a herd of sheep, we have a herd of sheep that's blocking the car, right?
Yeah, the residual information that is in the objects that are cropped is lost after the aggregation. If you can have a residual path or something that brings this information after the aggregation, and the predictor can also see that. Yeah.
There's no preferential system here, right? Every patch looks the same to each other once they're in the bottleneck. There's no preferential reference. So if there's some relationship that it matters between them, it's impossible to capture. The patch should come at the beginning or at the bottom. Yeah, but that's super interesting. I actually agree with that. Definitely worth exploring.
Yep.
Another thing that I did have in mind, and I imagine this came in the reviews. So, interventions. How are you doing here?
I mean, depending on what you want to do, like if you check at the, or if you intervene already on the individual object level things, then I mean that directly translates to the prediction. If you only want to intervene on the aggregate thing, then I mean it's difficult to trace it back to like the individual objects, right? But on the other hand, then it's also then like if you want to intervene on the aggregate concept space, then you, for example, say, okay, there are no, I don't know, no sheep in the image, which already like is a way, like from a semantic point, way bigger, I guess, intervention than just intervening on one individual object and saying, okay, this object is not a sheep.
But potentially here, there is also another kind of intervention, right? Like you can intervene not just on the concept activations, but you could intervene on the cropped images. You can swap to like a patch of an object with another patch.
True.
You can swap like a sheep for a cat and see what it's like. You can, and like if you like again, as we discussed earlier, like if you have a way to bring this information to the predictor, this could also have an effect on the task, like a deeper effect. Yeah. And have you experimented with like object level interventions, or like
we didn't explore many interventions, like yeah, so yeah. But yeah, the kind of like proposal intervention, let's say, is an interesting thing. I don't think we considered that so far, but it makes sense. I guess it's also kind of easier from like user perspective. I mean, just say, okay, like here in this part of the image, there's also something which hasn't been considered, right?
Okay, you can even download an image, just substitute it.
True.
There's lots of things that you can. I like this. It's a good initial step when you have all this stuff that you can go from it. To be honest.
Yeah, I think also the motivation of this work was not okay, this is a finished method which like solves everything, whatever, but it's more like, okay, we should probably go into this direction and explore into this like more structured, more concept representation, more complex tasks. And this is just like a very first, I would say, step into how to potentially start tackling this. And yeah. I'm sure this is far from solving it.
Yeah. Also, it reminded me of like very different in how it's done, but there was the concept transformers one, right? They do generate almost per patch prediction because they operate using VATs. So they patch up the image, and every patch of the image becomes its own token, like in our VAT, and they make contemplations at that resolution. Which is similar to this, except that the patching is done just very geometrically, right? It's like we're gonna patch in and wait, or we're not gonna do anything fancier than that. This seems to actually be more object-centered, but
we briefly compared OCB to using just patch level or like a different work which uses just patch level granularity. And I mean, if you have actually a task which is object-centric in some sense, I mean, kind of as expected, including object proposals instead of, or for concepts instead of just using general patches, makes more sense and does better.
It also works better generally. I would be surprised if it's not the case. Use the objects. All right, we probably have time for one more question before I know David has to catch a train. So, is there any last minute questions before we shut this down? Thank you so much. I really appreciate it. This was fantastic. Very good talk. Yeah, thank you.